Welcome to today's paper reading. Today's paper is titled Medusa, Simple LLM Inference Acceleration Framework with Multiple Decoding Heads. This paper, published in the Proceedings of the 41st International Conference on Machine Learning, introduces Medusa, an efficient method for accelerating large language model (LLM) inference by adding extra decoding heads. The authors, including Tianle and Yuhong from Princeton University and the University of Illinois Urbana-Champaign respectively, propose a framework that leverages parallel processing to reduce decoding steps and improve inference speed. The abstract highlights the challenges faced by large language models, LLMs, in decoding, particularly the sequential computation requirement and the bottleneck caused by moving full model parameters from high-bandwidth memory, HBM, to the accelerator's cache. Existing methods like speculative decoding face implementation hurdles due to the need for a separate draft model. To address these issues, the authors introduce Medusa, an efficient method that adds extra decoding heads to predict multiple tokens in parallel. Medusa employs a tree-based attention mechanism to construct and verify multiple candidate continuations simultaneously, thereby reducing the number of decoding steps. The paper presents two fine-tuning levels for Medusa. Medusa 1, which is fine-tuned on a frozen backbone LLM for lossless inference acceleration, and Medusa 2, which is fine-tuned together with the backbone LLM for higher speedup but requires a special training recipe. The abstract also mentions proposed extensions to improve Medusa's utility, such as self-distillation and an acceptance scheme to boost the acceptance rate, while maintaining generation quality. The recent advancements in large language models, LLMs, have shown that the quality of language generation significantly improves with an increase in model size, reaching billions of parameters. However, this growth has led to an increase in inference latency, posing a significant challenge in practical applications. From a system perspective, LLM inference is predominantly memory bandwidth bound, with the main latency bottleneck stemming from accelerators' memory bandwidth rather than arithmetic computations. To address this, the Medusa framework introduces multiple decoding heads on top of the backbone model to expedite inference. These heads are fine-tuned in a parameter-efficient manner and can be added to any existing model, offering easy integration into current LLM systems. Figure 1 illustrates the Medusa framework for accelerating large language model (LLM) inference. It shows how Medusa adds multiple decoding heads to the last hidden states of the LLM, allowing for the parallel prediction of several subsequent tokens. During inference, each head generates multiple top predictions for its designated position, which are then assembled into candidates. These candidates are processed in parallel using a tree-based attention mechanism. The final step involves verifying the candidates and accepting a continuation. Additionally, a typical acceptance scheme is used to select reasonable continuations, and the longest accepted candidate prefix is used for the next decoding phase. The Medusa framework follows a three-step decoding process, generating candidates using Medusa heads, processing these candidates through tree attention, and accepting the candidates. For training, two main strategies are employed. Medusa 1 involves training with a frozen backbone model, while Medusa 2 involves joint training with differential learning rates to enhance accuracy. Additionally, the framework includes extensions such as a typical acceptance scheme to improve efficiency, self-distillation to generate training data, and an optimized tree construction method to maximize acceptance length. Figure 2 illustrates the application of tree attention to handle multiple candidates simultaneously. The example shows that the top two predictions from the first Medusa head combined with the top three from the second head create a total of 6 candidates. Each candidate forms a unique branch in the tree structure. To ensure that each token only attends to its predecessors, an attention mask is designed to allow attention flow only from the current token to its antecedent tokens. Additionally, the positional indices for positional encoding are adjusted to fit this structure. In this section, we present the experimental results demonstrating the effectiveness of Medusa across different model sizes and tasks. We evaluated Medusa 1 and Medusa 2 on Vicuna 7B and 13B models, showing significant speed improvements. Specifically, Medusa 1 achieved a 2.18x speedup on the 7B model and a 2.33x speedup on the 13B model. Medusa 2 further enhanced these results, reaching a 2.83x speedup on both model sizes. Task-specific speedups were also notable, with the coding category seeing a 3.29x speedup and the extraction category achieving a 3.62x speedup. These results indicate that Medusa significantly enhances inference speed across various tasks. Additionally, we assessed the viability of self-distillation using Vicuna 33B and Zephyr 7B models. The results on MTBench showed that while the Vicuna 33B model had a lower acceleration rate, it maintained comparable quality, suggesting that self-distillation can effectively preserve model quality while improving efficiency. Figure 3 illustrates the speed comparison between the baseline, Medusa 1, and Medusa 2 on Vicuna 7B and 13B models. On the left, Medusa 1 demonstrates over 2 times the wall-time speedup compared to the baseline, with Medusa 2 showing an even greater improvement. The right side details the speedup performance of Vicuna 7B with Medusa 2 across 8 categories from MTBench, highlighting the extraction category with the highest speedup at 3.62 times. This suggests that Medusa significantly enhances inference speed, particularly for tasks like extraction. Figure 5 compares the performance of Medusa using typical sampling against greedy and random sampling methods. The plot shows the acceleration rate and average scores on the writing and role-play categories of the MTBench dataset, with a fixed temperature of 0.7. Greedy sampling is represented by stars, random sampling by dots, and typical sampling by curves under different thresholds. As the threshold increases, there is a trade-off between quality and acceleration rate, with typical sampling providing a balance between the two. Table 1 provides a detailed comparison of various Medusa 2 models, focusing on their accelerate rate, overhead, and quality as evaluated on the MTBench. The table highlights the performance scores of these models relative to their original counterparts. Additionally, it lists the speedup achieved by Decoding and Medusa for each model, including Vicuna 7B, Zephyr 7B, Vicuna 13B, and Vicuna 33B. This comparison underscores the efficiency and quality preservation capabilities of the Medusa 2 configuration in large language models. Figure 4 illustrates the effectiveness of different numbers of candidate tokens for decoding introduced by trees. On the left, it shows the acceleration rate for randomly sampled dense tree settings, blue dots, and optimized sparse tree settings, red stars. The right side displays the speed in tokens per second for both settings. The trend lines indicate that while the acceleration rate remains relatively stable for sparse trees, there is a noticeable decrease in speed as the number of candidate tokens increases. Table 2 presents a comparison of various fine-tuning strategies for the Vicuna 7B model. It highlights that Medusa 1, which fine-tunes only the Medusa heads, achieves a 2.18x speedup without compromising generation quality. In contrast, Medusa 2, employing two-stage fine-tuning, maintains quality while offering a greater speedup of 2.83x compared to Medusa 1. Direct fine-tuning with Medusa heads results in degraded generation quality, indicating that Medusa 2 is effective in maintaining model quality and improving speedup. Table 3 illustrates the impact of different techniques on the speedup of large language models, LLMs. The first technique, Medusa 1 heads without tree attention, achieves a speedup of approximately 1.5 times. By adding tree attention, the speedup increases to about 1.9 times. The most significant improvement comes from using an optimized tree configuration, which results in a speedup of around 2.2 times. These results highlight the effectiveness of each technique in enhancing the inference speed of LLMs. Medusa, an innovative method for improving the inference speed of large language models, LLMs, has significant implications across society, technology, and ethics. Socially, Medusa enhances accessibility and democratization of AI, potentially leading to innovations in education, healthcare, and entertainment. It also contributes to environmental sustainability by reducing energy consumption. Economically, Medusa lowers the cost of deploying advanced AI models, fostering growth and competition. Technologically, Medusa accelerates inference speed by 2.3 to 2.8 times, is parameter efficient, and easily integrates into existing systems. Ethically, it raises concerns about bias and fairness, the need for transparency and accountability, and potential security and privacy issues. Ensuring these ethical considerations are addressed is crucial for the responsible deployment of Medusa. Thank you for watching.